Right, we've already come across solving equations with unknown powers in the index, and we learned how to use rules of indices to solve it. So, for example, if you were asked to solve the following equation, 4 to the power of x equals 4096, you'd ask yourself, what could I write them as powers of? Now, you could write 4096 as a power of 4, just use trial and error on the calculator. But let's say it couldn't be written as a power of 4, then you'd say, well, what else could it be written as? Like 4 could be written as a power of 2. So can 4096. So that's probably what I would do. But it is quicker if you realise that 4 to the power of something would actually give you back 4096 straight away. Okay, but anyway, we'll go with 2, right, and break it down. So if I can write everything as a power of 2, that's what I'm going to do. So 2 squared would give you back a 4. And then trial and error on the calculator, you'd eventually figure out that 2 to the power of 12 is 4096. Then we apply rules of indices. Power to a power means you'd multiply. So that would become 2 to the power of 2x is now equal to 2 to the power of 12. And at this stage, when you have the two base numbers, the large numbers the same on either side of the equals, you can let the powers equal each other. So 2x must be equivalent to 12. So create a new equation, 2x equals 12, divide across by 2, and you will get x is equal to 6. So I've now found my solution for x, and I can check if that's correct. So if I sub it back in to the calculator, okay, so it was 4 to the power of 6. What does that give me back? I get 4096. Okay, but that was okay because we were able to use rules of indices to solve that equation. What if you couldn't use rules of indices? So let's say the equation was 4 to the power of x equals 193. There is no number I'm going to be able to write 193 as a power of straight away. Like I can write 4 as a power of 2, but like 2 to the power of nothing is going to give me back 193. So I'd be stumped. I couldn't use rules of indices. So you have to be able to solve it. So this is where we use logs instead. Okay, we would introduce logs. Okay, so I'm going to do the first question again, but I'm going to use logs to solve it as opposed to using rules of indices. Okay, so the equation was 4 to the power of x equals 4096. Now, I want to solve it, even though, let's say I didn't realise that I could use rules of indices to solve this. Okay, that's fine. I'm going to introduce logs instead. As long as you introduce to the left-hand side of the equation the same log that you introduced to the right and keep the equation balanced, then we're okay. The easiest log to introduce would be, look at the base number here. So we have a base of 4. The quickest and the easiest log base to introduce would be a log with a small base of 4. Okay, that's the quickest one. It's like I could introduce any log base, but the quickest one will be this one because the large base number was 4. What you do to one side of an equation, you have to do to the other to keep it balanced. So if I get the log of base 4 on the right hand side as well. Okay, now we then apply rules of indices. In the log tables, the rule for when the base number is the same as the small base number, your answer is just going to be the power. You'd be left with x. So what power would I put 4 to get back 4 to the power of x? You'd put it to the power of x. So your answer is x, and that comes from one of the rules in the log tables. And then you just go to your calculator to type in log 4096 with a base of 4. Okay, so there's a log button here on the calculator. All right, log, put in the little base of 4, put in your 4096, press equals, and I get back 6 straight away. Okay, and that was the same answer we got when we used rules of indices instead. Now I'll come back down to this one, right? There is only one way to solve this, and I have to introduce logs, whereas obviously there was 2 methods of solving this equation. I could either use the indices method or I could use the logs method. The logs is quicker. With this one, you can only use the logs method because I can't write 193 as a power of 4 or I can't write it as a power of 2. Whereas I can write 4 as a power of 2, but if you can't do to both, there's no point. So I introduce logs. Again, the base number is 4, so I'm going to introduce a log with a small base of 4, and what I do to one side, I have to do to the other side to keep it balanced. One of the rules of logs, if the large base number is the same as the small base number, your answer is x. And then I can put this into the calculator. Okay, so I press the log button. All right. Log 193 with a base of 4, and I get back 3.79622. So I get a big long decimal as my answer. You can check if that's correct. If I'm now saying that x is equivalent to 3.7966, I can just put 4 to the power of that number and see what I get back 193. So It was the last thing I did on the calculator. The calculator holds that answer. So if I clear the screen, 4 to the power of the answer I just got, 193. So I know I'm correct. Here's another example. Solve for x. So 3 to the power of x is equal to 61. I know I can't use indices to solve that. You can't write 61 as a power of 3, and you can't write 3 as a smaller breakdown of any other index. So I have to leave it as it is. So I'm going to introduce logs. Because the large base number is 3, I'm going to introduce log with a base of 3, and what you do to one side, you have to do to the other. Log 3 to the power of x base 3 will just leave me with x, and I can put that into the calculator. So log 61 base of 3 gives me back 3.741, and it goes on forever. And again, you can check if that's correct by subbing it back in. 3 to the power of that, and you'll get back 61. Right, so that was when I introduced log with a base of 3. I already said you could actually introduce any base at all, but whatever the big base number is, it'll always be quickest if you just introduce a log with that as a small base number. But again, I could have introduced any base number, so I'll show you the same question again, but I'll use a different base number. Okay, so what if I introduce a log with a base of 2 on both sides? Okay, that's still fine as long as I do to one side what I do to the other. But the reason why this will be a little bit longer than this is because I have to apply the rules of logs. Like the rule of log there was to just get x, because that's one of the straightforward rules from the log tables. But here I'm going to have to apply more than that. This isn't a straightforward rule, so what I'm going to have to do is bring my power of x down in front of the log. So now it would read as x times the log of 3 base 2 is equal to log 61 base 2. If I want to get x on its own, and x is being multiplied by the log of 3 base 2, well then in order to undo that, I need to divide by the log of 3 base 2. And what you do to one side, you must do to the other. Okay, then I can simplify. Log 3 base 2 will divide into log 3 base 2 above and below. So now you're just left with x is equal to, and I can put the right hand side into my calculator. And I get back 3.7418, which is the exact same answer that I got up here. But it just shows that I have a tiny little bit of extra work to do because I introduced a log with a base of 2 as opposed to the log with the base of 3. So that's quicker. It was literally one step. This ended up being 2 steps because you had to apply further rules of logs in order to get x on its own. Again, just to show you, what if I introduce log with a base of e? So the natural log, ln, on both sides. So that's log with a base of e, but we call it ln for short. Again, I'm going to have to apply my rules of logs. So I would bring the power of x down in front, so it'll be x times ln 3 is now equal to ln 61. And I want to get x on its own, so I have to divide across by ln 3. As long as you do to one side what you do to the other, we're keeping it balanced. ln 3 divides into ln 3 once, so it's gone. You're left with x is now equal to, you put that into your calculator. So ln 61 all over ln 3, so you're just using your natural log button, and you're getting back 3.7418. So exact same answer again. All right, but again, it was the extra line of work. So it is always going to be quicker if you introduce a log with the same base as the large base number. The only time where there is a restriction on what you can introduce is if it was an inequality. Now, these were all equations, okay? But if it was an inequality, you have to introduce ln. That's a rule. Okay, so that's just a particular rule, and it's only applicable to inequalities. For any equations, you can introduce any base at all that you want, and it'll always work. But for inequalities, the one that works, which means you won't end up with a mistake with your final answer, it's the natural log, ln, that you have to introduce. So just to show an example of that, if I was asked to solve 2 to the power of x is less than 9. Okay, again, unknown power in your index, so I would introduce logs. But because it's an inequality, I have to introduce the natural log, ln, on both sides. Okay, then I just apply my rules of logs. Bring the power of x down in front of the log. I want to get x on its own, so now I have to divide across by ln2. But remember, it's inequalities, and when you're working with inequalities, if you multiply or divide across an inequality by a negative number, the sign has to flip around. So I'd need to check, before I go dividing both sides by log 2, I need to check if log 2 is positive or negative. So a quick check on the calculator, ln2, and I get back a positive answer. Okay, so that's grand. That means if I divide across now by ln2, I am dividing across by a positive number, which means my inequality symbol doesn't need to flip around. ln2 divides into ln2 once, so it's gone, so you're left with ln 9 all over ln 2 on the calculator, 3.16. So x is less than that value. Now, if they tell me x is a natural number or an integer, or, they could tell me anything about what kind of a number x is. Let's say x is a natural number. Natural numbers are positive whole numbers only starting at 1. So if I'm told that x is less than 3.1699, well then the only possible values x would be 3, 2 or 1. If it has to be less than 3.16, well then the next possible integer is 3, it could also be 2, or it could be 1. And you can check if that's correct. If x was 1, would the inequality hold true? Would 2 to the power of 1 be less than 9? Yes, it would. You can check for 2. Would 2 to the power of 2 be less than 9? Yes, it would. And you could check for 3. Would 2 to the power of 3 be less than 9? Yes, it would. So your inequality holds true. Okay? Alright, so always get in the habit of checking afterwards to make sure your inequality still holds true. One more quick example. If you're asked to solve the following, 1/2 to the power of x is greater than 10. Let's just say you forgot that you have to use the natural log. When it's inequalities, you must sub in the natural log, okay, or introduce the natural log. Let's say you forget and you decide to introduce a log with a base of 1/2 because the large base number is 1/2. I'll just show you why you won't get the right answer, okay? So I've introduced a log of base 1/2 on both sides. I have to then tidy this up. So the log of 1/2 to the power of x with a base of 1/2 will just leave me with x is greater than. I'll put that into the calculator. And I get back minus 3.32. Okay, and let's just say we were told that x had to be an element of the integer, so it's positive or negative whole number. Well, if x has to be greater than minus 3.32, think of your number line where minus 3.32 would lie. It would lie roughly, around here. So if I'm supposed to be greater than that, I should be to the right of that number line, okay? So that would mean the next possible integer would be minus 3. It could also be minus 2. It could be minus 1. It could be 0. It could be 1, 2, 3, 4, 5 up to infinity. Okay? I can't be equal to the minus 3.32 because the sign said greater than. And I have to be an integer, so I have to be a whole number. So that means x could possibly be minus 3. Could be minus 2. Could be minus 1. 0, 1, 2, 3, 4, 5. Okay, up to infinity. Now, I'll just show you why this is not the correct answer. I'm going to do it with the introduction of the natural log, and I'll show you how I get a different answer. Okay, so put down the inequality again, and I'm going to introduce ln on both sides. Okay, apply my rules of logs, bring down the power of x in front. I want to get x on its own, so I need to divide across by log 1/2. Remember, it's inequalities, so check to see whether log 1/2 is positive or negative. It's negative. Okay, so I now know that I am dividing across by a negative number, which means the inequality symbol is going to flip around. So ln 1/2 will divide into ln 1/2 once, so it's gone. You're left with x is now going to be less than this. And I'll put that into the calculator. Okay, and you get back minus 3.32. So x is less than minus 3.32, and it goes on forever. And again, let's just say we said that x was an element of the integers. Well, now if I am less than minus 3.32, go back to my number line. Being less than it, so here's minus 3.32. To be less than it means you'd be going further back on the number line. So the next possible integer it could be is minus 4. It could be minus 5. It could be minus 6, down to negative infinity. I'm getting the opposite answer than I got up here. Okay, this is the correct answer. That is the incorrect answer. You'll get a temp marks, but you won't get your full marks out because your inequality symbol ended up being the wrong way around. So that's why the rule of thumb holds. When you're dealing with inequalities, you always have to introduce the natural log if you've got unknown powers in your index. But if it's an equation, okay, like it was with our other examples, these were equations because it was an equals, you can introduce any log to both sides and it will work. Okay? Right, so that's how we introduce logs in order to solve equations with unknown indices, where you're not able to use indices, rules of indices to actually solve it. You can just use logs. But you could use logs all the time, even if you could use indices to solve it, like with our very first example, which was that one. Okay, so I had two methods to solve that one, whereas with this one, I could only use the log method, introducing logs.